For over 60 years, software engineering has operated on a single, unbreakable rule: determinism. Whether you use functional programming, procedural methods, or object-oriented architectures, the contract is identical. You provide an exact set of instructions, and the machine produces the exact same output every single time. This timeline illustrates how we arrived here. Agentic coding relies on these historical methodologies, acting as a new layer of abstraction on top of that rigid foundation. But this introduces a paradox. Unlike the code it writes, an agentic system is inherently non-deterministic. Feed the exact same prompt to different base models or execution frameworks, and you will get wildly different architectural choices. Correct input no longer guarantees predictable output. The scope of AI assistance has moved past writing isolated functions. We now deploy agents to execute autonomous, multi-step workflows. To survive this transition, your role has to change. The software developer must shift from an individual contributor writing syntax to a systems designer. Because the execution is non-deterministic, you have to build strict deterministic constraints around the agent to guide it. Without a rigorous architectural framework to contain the AI, an autonomous agent will quickly corrupt a stable codebase. Your value is no longer in typing the code, but in orchestrating the system. Look at this isolated node. At the bottom of this stack is the base model, engines like Claude, GPT, Gemini, or a locally hosted Llama instance. Think of the model as a stateless brain. It has read almost every open-source repository on Earth, but it has absolutely zero awareness of your specific project. If you want to manage this system effectively, you have to understand its personality. Treat the model like a brilliant, overeager new grad with a PhD, but no real-world experience. It is highly overconfident. It is eager to please you, and it lacks architectural judgment. To bridge this gap, the model relies on the context window. This bounding box acts as its only mechanism for short-term memory during a working session. This memory is measured in tokens. A token is roughly equivalent to a word or a fraction of a word in text processing. Modern models boast context windows that can hold 1 million tokens or more. But that massive capacity creates a trap. Bigger context windows are not inherently better. If you feed the model massive amounts of stale, irrelevant project history, you will confuse it. The performance severely degrades as it tries to reconcile old decisions with new instructions. Unlike a human engineer, the model does not naturally filter out old or irrelevant data as the project evolves. Managing this token economy is your primary job. If you fail to rigorously curate the context, you guarantee the agent will hallucinate. The base model can understand your instructions, but on its own, it cannot actually do anything. This new perimeter ring represents the framework. Tools like Claude Code or Codex provide a layer that gives the model the agency to read files, write code, and execute terminal commands. When you combine the model, a curated context, and an execution framework, you get a specialized coding agent. However, every time you spin up a new session, you hit the blank slate problem. The agent boots up with total amnesia regarding anything you did yesterday. To solve this, you use a primary initialization file, typically named agent.md. You use this file to bulk load the exact necessary context straight into the workspace on startup. As the project moves forward, you must continuously update and aggressively prune this agent.md file. This is how you avoid the too much information trap we just discussed. When feeding the agent this context, avoid binary formats. Agents cannot safely or natively parse binaries like PDFs or Word documents. Instead, stick to the lingua franca of the AI stack, plain text, specifically Markdown files or JSON format. JSON, or JavaScript Object Notation, is a standard text format used to store structured data. You organize these text files into living documents within your repository. These files act as constant state trackers that the agents read upon initialization. In an agentic pipeline, these structured living Markdown documents are just as critical as the application code itself. They act as the control rods containing the AI. To execute a complex multi-step task, you need to prime the agent using specialized plan modes. While in plan mode, the agent is restricted. It cannot alter the codebase. It is confined entirely to writing architectural blueprints. This creates a mandatory human checkpoint. Before a single line of code is written, you must review, modify, and approve the generated blueprint. Once approved, you break that complex blueprint down into discrete, highly portable stages. We call this phasing. Phasing allows you to stop a session mid-project and resume it later. You can even hand the exact same context off to a completely different model to pick up where the last one left off. This portability unlocks the ability to build multi-agent teams, where multiple agents work simultaneously on different facets of a single larger project. This diagram illustrates the specific mechanism to achieve this concurrency, the Git worktree hack. A Git worktree is a feature that allows you to check out multiple branches of a single repository in different directories simultaneously. By utilizing worktrees, you spin up separate agents inside isolated environments, letting them build discrete stages of the plan at the exact same time. Eventually, those concurrent worktrees must be merged back into the main branch. Standard merge conflicts will occur, requiring either you or an agent to resolve them. Scaling an AI team focuses on building a parallel orchestration engine, effectively turning one developer into a multi-threaded engineering manager. Operating this engine requires navigating the smart-stupid paradox. Agents are capable of profound leaps of logic, yet frequently fail at basic, obvious tasks. This looping animation illustrates the most dangerous failure state, the flailing loop. Agents are highly mission-oriented. When they hit a hurdle, they try to find a workaround. Because they lack judgment, agents blindly iterate on bad ideas, endlessly pushing failed workarounds instead of stepping back. Human interruption at this stage is absolutely mandatory. To mitigate this, apply a strict prompting guardrail. Always frame complex tasks with rigid bounds, commanding the agent to stop if you run into problems. You also need a trust but verify pipeline. Continuous regression testing is the true backstop against a non-deterministic codebase. You can deploy advanced verification topologies, like AI pair programming, where a secondary agent cross-checks the primary agent's outputs. Even with these systems, we still face the nanny problem. Operations that are potentially destructive still require constant human verification, which creates an unsolved bottleneck in the workflow. Despite these friction points, the economic viability of professional agentic coding is clear. Strategies like subscription hopping across providers for roughly $20 to $100 a month deliver massive returns for experienced developers. The industry is still in its infancy. The methodologies are actively being invented, and the tools remain highly experimental. But the verdict is clear. Because agents completely lack architectural taste and safety judgment, your job as a developer is safe. However, the days of hiring armies of new grads to write boilerplate code are over. The future belongs entirely to the managers of the machine.